For critical fields, I mean, think engineering, physics, where precision is absolutely key. Relying on approximations means you're building on, well, a slightly fuzzy foundation.
Fuzziness. Yeah.
Imagine trying to precisely model, say, quantum interactions or engineer something incredibly complex when your basic equations only give you close enough answers. These little inaccuracies, they add up.
The deeper you go, the worse it gets.
Exactly. Your results become less and less reliable.
Okay, but what if that impossible barrier just, well, wasn't there anymore? What if it just dissolved?
Now you're getting to it.
Today, we're diving into Ezouidi's theorem, and it sounds truly revolutionary, a new method that promises exact symbolic solutions for these complex equations.
It really is. It's a fundamental rethink, potentially, of what's actually solvable in algebra.
So this isn't just like a neat new mathematical trick.
Oh, no, much more than that. It's about a potential shift in our ability to get precise, true values, not just educated guesses.
Okay.
So, our mission in this deep dive is basically to unpack the principles behind this theorem. We'll look at how it tackled a really challenging 16th degree polynomial.
A degree, 16. Wow.
Yeah. And we want to show why its precision really changes the game compared to, the classical methods. So for you, the listener, you're getting a direct pathway to understanding this potentially groundbreaking advancement.
And this is all based on the research paper laying out the theorem.
That's right, drawn straight from the foundational paper detailing Ezouidi's theorem and its applications.
Okay, let's get into it. So before Ezouidi, what were the main options? If you had one of these really high degree polynomials.
Well, often you'd turn to numerical methods, things like Newton's method, for instance.
Right, I remember that from calculus.
Exactly, and they're powerful, no doubt. But the key thing is, they only give you approximations of the roots.
Close, but no cigar.
Pretty much. And with every step in the calculation, especially with these long, complicated polynomials, you risk accumulating rounding errors. You just can't guarantee a perfect, absolutely exact answer.
Okay, so that's the practical limitation. What about the theory?
Yeah. Well, then you run into a deeper theoretical hurdle, something called Abel's theorem.
Abel's theorem.
It's a really foundational concept in algebra. And it famously states that certain polynomials, quintics and higher in general, simply cannot be solved using radicals.
Using radicals, meaning like square roots, cube roots, that sort of thing, added, subtracted, multiplied.
Exactly. You can't find their roots just using basic arithmetic operations and taking nth roots. It was seen as a definitive statement of limits, a hard boundary.
That sounds pretty fundamental. So where does Ezouidi's theorem fit in? Does it like find a loophole in Abel's theorem, or is it doing something completely different?
It seems to be taking a different path entirely. Ezouidi's theorem doesn't just find a clever workaround. The claim is that it directly shows how to get exact, symbolic solutions, even for problems that Abel's theorem suggested were unsolvable with radicals.
Ooh.
It's like finding a completely new road around that brick wall we talked about. It reveals exact solutions where we previously thought only approximations or, well, nothing solvable by radicals existed.
So it's not contradicting Abel's theorem directly, but offering a different kind of solution.
It's providing exact solutions, but perhaps not necessarily expressed purely in terms of radicals in all cases. The method yields symbolic solutions, which might involve other functions or forms, like complex exponentials, as we'll see. It fundamentally shifts the perspective on solvability.
That's a really significant claim. Okay, so how does this mathematical engine, how does it actually work? What's the core idea?
Well, at its heart, Ezouidi's theorem transforms the polynomial problem. It turns it into a systematic, recursive process.
Recursive, meaning it builds on itself.
Exactly. You can sort of picture a mathematical assembly line. At each step, it precisely calculates certain components, these symbolic coefficients, building towards the exact roots without any guesswork or approximation.
So it's the systematic nature that avoids the errors.
Precisely. It inherently sidesteps all those rounding errors and inaccuracies that creep into numerical methods, which is a fundamentally different way of extracting the answer.
And there's a specific recursive formula involved, right? We don't need every detail, but can
Mhm.
you give us a feel for what's happening inside that formula? What kind of math is it using?
Sure. Think of it as having different mathematical tools or building blocks within the formula. You've got things like binomial coefficients, those CNR, NR prime
Mm.
terms, which kind of act like adjusters, tailoring the calculation to the polynomial structure.
Okay.
Then there are terms that involve powers of coefficients like LBOQ and Nash S0R. These manipulate the polynomial's degree and base coefficients in specific ways.
Hmm.
And crucially, there are terms like SK1R, which refer back to coefficients calculated in earlier steps of the recursion. It's constantly refining things based on previous precise results.
So it's this step by step precise calculation using these symbolic pieces that guarantees the exactness.
That's the core idea. It systematically works through the polynomial, calculating these special scalar coefficients with absolute precision at each stage, ultimately leading to the exact symbolic roots. No approximations needed.
Okay, let's make this concrete. The paper uses a really tough example, right? A 16th degree polynomial.
Oh, yeah, it's a beast. The full equation is, well, it's long. We can put in the show notes for anyone brave enough.
Please do. Just imagine this long string of x raised to the 16th, 15th, 14th power, all the way down, with huge coefficients. Solving that exactly using traditional algebraic means. Forget it.
Generally considered impossible, exactly. But here's where the theorem really shows its power. When Ezouidi's theorem was applied to this specific monster polynomial,
Yeah.
something quite amazing happened during the calculation of those symbolic scalar coefficients.
What? Did it simplify somehow?
Dramatically, almost all of them
Big
just
line?
turned out to be zero.
Seriously? Zero.
Yes. Out of all the potential scare values calculated through the recursion for this specific polynomial, almost every single one vanished. Zero year, S1R, S2R, all the way up to S14R, except for S7R, were just zero.
Wait, so 0 through S6 were 0. S8 through S14 were 0. That's
Yeah,
nearly all of them.
exactly. It means that this incredibly complex looking polynomial, when viewed through the lens of Ezouidi's theorem and these scalar coefficients, had a much simpler underlying structure for its solution.
So what was left? Which ones weren't 0?
Just two key ones, really, that drove the solution for this particular equation. There's a 7r, which came out to be n to the 12th, 860 times 16 to the power of 8.
Okay.
And then S15r, which was n 1070,000 times 16 to the power of 16. Huge numbers short, but only two significant terms emerging from that whole recursive process.
So the original massive equation boiled down based on just those two numbers.
Essentially, yes. The transformed equation, expressed in terms of a variable related to x and these scalar coefficients, simplified dramatically. It became something like some function of by 16 minus the S7R constant times some function of by 8 minus the S15R constant equals 0. Much, much simpler.
That's incredible. It's like the theorem found a hidden simplicity.
It did for this example.
Yeah.
And from that simplified form, the roots can be derived. The paper also briefly mentions calculating another related term, S1R Cartier, which involves these non-zero coefficients, confirming the structure.
And the final roots, how are they expressed?
They are derived recursively and ultimately expressed as complex exponentials.
Ah, so not necessarily simple radicals, but exact symbolic forms using exponentials.
Exactly, which is a very powerful and elegant way to represent solutions covering both real and potentially complex roots, and it emerges directly from this precise symbolic process.
So let's hammer this home. The absolute core message here is exactness. This theorem isn't about getting close enough.
Not at all. It delivers the precise true values for the roots, symbolically.
Why is that such a massive deal? What's the real difference compared to getting a really, really good numerical approximation?
The difference is certainty versus estimation. Numerical methods, however refined, always carry some margin of error, some potential for rounding issues to accumulate. It might be tiny, but it's there.
Right.
In fields where tiny differences can have huge effects, think quantum mechanics, designing complex molecules for pharmaceuticals, long-term simulations in astrophysics, that small margin of error can snowball into significant deviations from reality.
So getting it slightly wrong early on leads to being very wrong later.
Potentially, yes. With Ezouidi's theorem, the claim is you're not just getting closer to the truth, you have the symbolic truth. It's potentially a leap from estimation to, well, actual knowledge in solving these equations.
And you mentioned it tackles polynomials that classical methods deemed unsolvable in a certain sense. Beyond the pure math breakthrough, what does this unlock? What are the potential real-world applications for us listening?
Well, think about it. Fields that rely heavily on complex modeling, cryptography, for instance.
Okay, how so?
The security of a lot of modern encryption relies on the difficulty of solving certain mathematical problems, sometimes related to factoring large numbers or discrete logarithms, which can connect back to polynomial-like structures.
If we suddenly have a new, powerful tool to solve complex equations exactly.
It could lead to stronger encryption, or maybe break existing codes.
Potentially both. It could open avenues for developing more robust encryption methods, but also might provide tools to analyze the vulnerabilities of current systems. It changes the landscape.
Interesting. What else?
Material science, designing new materials often involves understanding atomic bonds, crystal structures, things described by highly complex equations.
Right.
Exact solutions could allow for the design of materials with properties we can currently only dream of, maybe super efficient solar cells or incredibly strong lightweight composites or perfect catalysts. Precision matters hugely there.
And maybe even finance, modeling markets. Absolutely. Financial modeling uses incredibly complex equations too. And even tiny errors in prediction models can lead to massive real world consequences. More precise solutions could lead to more accurate risk assessments, maybe more stable economic models. It really could elevate our ability to model and innovate across so many disciplines.
It's clear the implications are potentially huge. So, just to bring it all together then, Ezouidi's theorem looks like it represents a really profound shift
It does, a shift away from just accepting good enough approximations for many complex polynomial problems.
towards delivering exact symbolic roots. It fundamentally changes what we thought was mathematically possible, or at least how we achieve solutions.
Exactly. This deep dive, hopefully, has given you a front row seat to what might be a pivotal moment in algebra. We're seeing how problems once considered, effectively out of reach for exact solutions are now potentially yielding to precise analysis.
Opening up entirely new
New
frontiers.
frontiers in understanding mathematics itself and definitely in its application.
So, here's something to think about as you go about your day. A final thought for you, the listener. If we can now find exact symbolic solutions for problems previously thought unsolvable or only solvable approximately, what other long standing mathematical or maybe scientific challenges are just sitting there waiting?
Waiting for a similar kind of revolutionary breakthrough.
Yeah. What other problems that we currently label unsolvable or too complex are just waiting for their own Ezouidi's theorem to come along and unlock their secrets?